So I'm really glad to follow the previous talks because much of what I was going to say has already been said. I'm trying to find things to disagree with. I'll find a few. But what I want to do is come back to this interplay of systems engineering and software engineering. That's what's brought us here. And so in the interest of concreteness, I want to start with a small example of what can go wrong. Imagine you're on the New Jersey Turnpike. Has anybody been on the New Jersey Turnpike? Okay. And so you're in that zone of the turnpike where there are 3 lanes, and you're driving in one of the lanes, and somebody else drives the far lane, and you're in the slow lane behind a big truck going up a hill. So you look over your left shoulder and contemplate moving into the center lane. Meanwhile, somebody in a zippy sports car is off in the left lane behind somebody who's talking on their cell phone, and they're thinking they're going to come around them on the right. So they look over their right shoulder, and you're looking over your left shoulder, and you both see that the center lane is clear, at which point you both move out, right, with the obvious consequence. And so this is called a check-then-act race condition. It's a familiar situation on the highway. It's also a familiar situation in concurrent and distributed systems. Even on the screen of a mobile device, you can have a race condition between the human user and the app itself. You've all had the experience of ending a phone call. Well, but the person you were speaking with ended the call just a moment before you did. So when your finger touches the screen, it's touching something that you did not intend it to touch. Okay, and so this is in the world of security, this is sometimes called TOC2, T-O-C-T-O-U, time of check to time of use. It's a security issue. It's been exploited in many ways. OpenSSH is an example of that. And so as a consequence of this kind of consideration, we have all these devices of monitors and locks and queues and waiting and blockage. And if you look at programming languages have constructs to deal with this, or they have libraries to deal with it. If you look at large-scale systems, for example, when you have collaborating or coalitions of interacting systems, this is something we pay attention to. And my point is that this is an issue at every level of scale, from a single multi-core chip up to systems of systems, where we can let the data get out of sync because of race conditions such as this. Okay, and there are many pitfalls of concurrency. So once we start trying to use the locks, then immediately we open ourselves up to the possibility of deadlocks, of state inconsistencies, of blockages and excessive waiting. And so these are further consequences. And these deadlock, for example, is a global property of a system. There's no one place to look to find where the deadlock is going to happen. Okay, and so the question is, how can we handle this kind of an issue from a systems perspective? Okay, and so there are many parts to that answer, and I want you to think about what those parts might be. Obviously, there are issues at the architecture level, policies that we can set, for example, block orderings, policies for deadlock avoidance is one case, but also there are modeling and analytic approaches that we can take. We do this often for software. It's a key feature of protocol design. And also we can integrate into our process and our practices discussions even at the earliest stages of requirements gathering, or at stages when we're starting to think about making assurance cases, considerations that relate to this kind of issue. I really like this category of example. And one, because it exists at every level of scale, but two, because some of these errors are in the category of the 1 in a million case, right? There's a stochastic characters. Several of you have already mentioned stochastic modeling. Why do software people care about that, right? Well, there is, once you get concurrent, you have you have non-determinism and asynchrony. We have to start thinking in that way. And you could say, well, there's a 1 in a million chance that particular interleaving of events is going to occur where you get that data corruption. And so you've got a 1 in a million chance of your test case nailing it. Not so much. Oh, and it's also sort of a global property, so your inspection practices aren't going to help you find it either. But you know, you've got it in your data center and you've got it running on 10,000 cores and it runs 1,000 times a second. So that means 10 times a second, you've got a very high likelihood of getting zapped by this thing. And you eventually have to push the big red button because you've got data corruption there. Okay? So it's challenging to model, it's challenging to assure, and so it's instructive for my purposes today. Okay, so my story today basically is a story about this inevitable, unavoidable intertwining. I've told that story. Now I'm going to talk in a more philosophical way about this essential affinity of systems engineering and software engineering. And I want to do this in a sort of a theoretical mode. I'll get back to concreteness in a moment. And the concreteness is going to be with respect to the particular levers that we apply. And the interesting thing about these three levers, besides the fact they all begin with the letter A, which makes it easy to remember A, right, is that they are common to the discussions we've had all throughout this morning. Okay, and so I want to come back to those and understand a little bit about why that commonality exists. So here's my proof on one slide. Right, and it's a lot of words. You can see the headline over here, and you can see the tail line over there. Right, and so the headline is, well, let's start with systems engineering. Systems engineering, to put it in one line, the bumper sticker, I would say, is it's engineering management in an environment of complexity and uncertainty. If we actually had certainty, or if we didn't have much complexity, then we would just do it and get it done, and we wouldn't have to talk about our doing of it because it would just happen for us. It's the complexity and uncertainty that causes us to think about how we do it, and even to get to the point of trying to systematize the practice of how we do it. And so it's important to understand what kinds of uncertainties we deal with, right? Uncertainties regarding the structure of the thing. What engineering media do we use? How do we migrate functionality out of hardware and into software? How do we migrate functionality from humans into systems, or the other way around? Okay, so all those kinds of trades. What about requirements? Do we know actually what we want to build in advance? Do we really fully understand the mission environment or the threat? Do we actually fully have a predictive model of the infrastructure on which we will base our system, whether it's civil infrastructure or vendor components or what have you? And also, do we really understand what are the quality attribute requirements? I'm using Kevin's term. We don't try not to say non-functional requirements. It confuses people. Because, I mean, we know the systems don't work, but let's not reinforce that fact. So we really want to talk about the full range of different kinds of quality attributes. What I want to say is that there's an essential character to these uncertainties. Essential not in the sense that we want it and need it, but essential in the sense it's of the essence. Okay, and the of the essence is that we don't know how to measure everything. We have a terrible light under the lamppost problem. And so we are forced to make expert judgments all the time. And we should never discount the value of expert judgments, especially in cases where we haven't yet figured out how to create the measurement. And that's a hard research problem that we all should be facing, is building new lampposts. Okay? And the best lampposts come from semantically based models. You want to understand the concurrency characteristics of your system? Base it on a semantic model that we can actually reason about and understand. Not about diagrams, obviously. And the other essential uncertainty is, do we actually really have a predictive model of what are the mission requirements? What is the customer going to want a year from now? What's the supply chain going to look like a year from now? Okay, so that's my first set of bullets up here. Now to software engineering. I hope you don't mind my abbreviations. Software engineering, I mean, I'm paraphrasing Herb Simon. Herb Simon talks about the sciences of the artificial. He was already quoted once this morning. It's great to come from Carnegie Mellon. Talk about Herb Simon. But really, our business as software engineers is I would call it engineering the symbolic. It's not just the code itself. The writing of the code, we all know this. That's the least of it. The way we write the code matters a lot, but the models that we build and the practices surrounding that activity of writing the code, that's what's driving it. And the key thing about software, unlike other engineering media, one of the key things is it's not tied to any particular domain. It's not about electrical stuff or mechanical stuff or intelligence analytics stuff or imagery or whatever it is we're dealing with. It's meant to be general. It's meant to embrace the broadest range of abstraction. That's my point. That's exactly it. Thank you. Perfect. Okay? Right? And not just the abstractions that we already know and love, but the new abstractions that we haven't thought of yet. So in software, we talk about abstraction mechanisms. Object orientation is a school of thought regarding a particular approach to abstraction mechanisms. Okay? And just so you know, there are many such schools of thought, not just, there are others as well. Okay? And the question is, what's the nature of the generality that we create? What's the nature of what we can express? What's the nature of what we can reason about once we succeed at expressing it? Okay? And so software, because of this, and also because of its wonderful symbolic nature, has in fact, the reality is, it's the building material of choice. We always migrate functionality from other domains into software. Why is that? Why is that? Because the variable costs for software are nil. It's all in the fixed cost. Whereas in other engineering materials, we always have some variable costs. And we have statistical distributions on quality of production. In software, production is perfect. It's the designs that are terrible. Okay? And so, you know, the National Academy, the economists have asserted years ago that it was the largest single asset class, period, in the economy. Okay? And furthermore, some of you were involved with this study, critical code. It's changing quickly. This has already been pointed out this morning. There is no plateau in sight. Most important, the rapidity of change, the flux, is a key feature of why our operating environment is so challenging with software and systems. It's moving so fast. The boundaries between what we do and what we're wanting to do is moving quickly. So we don't succeed in systematizing. It's not just that the models are bad or we're building notations rather than models. It's also that it's a moving target, and we have to somehow come to terms with that fact. Okay? Software, I should say also, it's the material of cybersecurity. It's the stuff we build the defenses out of. It's the stuff that the offensive weapons are built out of, and it's the stuff that's being protected by those things. So that's why I say there's this essential affinity between the two. They both address this broad or unbounded set of abstractions. Okay, and they both, and this is now the second part of my talk. I could stop right now, but let me go on to the next part of the talk, because they both employ similar conceptual levers. And that's what I want to talk about next. Okay? And I'm talking about this again from the software perspective, so I hope you'll have patience with me in that regard, but it's the same, you know, AAA approach. Okay? And so AAA, to remind you, is architecture, what I'll call agility, which is really, and this is a point we made earlier, it's not always about just being as agile as possible. You know, if we're building a subsystem and it's amply precedented, the linear model is just fine. Okay, but it's being agile when we need to be agile. That's my point in calling it agility. And then finally, assurance, which is the whole range of quality-related issues. So architecture for software is much more than just the structure of the components. It's also invariance, it's semantical characteristics that we set to hold throughout the system. It's the rules of engagement in terms of meanings as well as actual structural features. Okay, so we divide. Why do we want architecture? We want to be able to operate at scale. We want to be able to operate concurrently. The only way to do that is divide and conquer. If we divide and conquer, then we want to minimize the extent of interaction among the team members and the small teams interacting with other small teams, because otherwise we have an unhappy situation with Metcalfe's law. Anybody know Metcalfe's law? Right? So the number of, if I have a network of a certain size, if I double the number of nodes in the network, then the number of interconnections among those nodes goes up as the square. Okay, that's why networks sort of inevitably overlap. It's the force of nature that the market can't overwhelm. That's why we have the internet. These are networks, interconnections of the network that were all extant many years ago. So with teams, if we have a team of 100 people and everybody needs to talk to everybody else, that's about 5,000 conversations. If I double the size of the team, the number of conversations goes up by a factor of 4. So that's why we want to minimize coupling and break things into components. Conway's law is very closely related to it. We want to, so that's the one piece. Second is we want to get to, as early as possible, some understanding of where we stand with respect to equality attribute requirements. Okay? If we get the architecture right, it's predictive of quality outcomes. Okay? But we want to get validation. Well, that's a real challenge to build the kinds of models that we did earlier. The other thing about architecture is we encapsulate variability. You don't know which mobile ecosystem you're going to use? Build a facade. That's a pattern. Somebody in the last session said that pattern. Build a facade, insulate the decision from the rest of the system. So you can change as you need to, and the consequences are localized. So those are all key features of architecture. Agility is about the process of how we enact it and how we make decisions, what commitments we make, when we make them. Right? Barry has talked about thinking of the process as a series of making commitments. It's a very important understanding. Okay, when do we want to make the commitment? When do we expect to be able to need to revise commitments? Okay, and so this is where we think about the activity of exploring engineering trade-offs. Finally, assurance, which has to do with evaluation and measurement, that whole set of things, is predicting and understanding the consequences of commitments that we might make or that we have made. And most importantly, doing that as early as possible, proximate to the time when we're contemplating that commitment. The worst case is what we used to call the requirements delay surprise model. 2 years of requirements, elicitation, 5 years of development, and surprise, that's not what we needed. Even if it were what we needed, it doesn't do the job, right? So that's one extreme, and the other extreme is we don't commit to anything, okay? So what we really want to do is concurrently create the system, the artifact, and the case to support any potential assurance claims we might want to make. And all of this is supported by the models that we build, the abstractions that we select, the way we reason about those models. You can't talk about reasoning about models if they don't have semantics. And the data we accumulate. The interesting thing about software engineering, when we think about it now as compared with a decade ago, is our discipline has become data intensive. We know, for example, if you go visit a developer site for a large open source system, and I suggest open source because it's out there to be looked at. Go to developer.mozilla.org. Look at the development of Firefox or Thunderbird. You'll see millions of lines of code. The heritage of every single line of code is understood and in the database. It's extremely granular, and there's tremendous amount of linking. That creates huge opportunity. Can we extend that into systems? Okay, so now I'm going to look at each of the three very briefly. So first about architecture, and I want to start with a sort of a centric angle on this, which is a statement from Admiral Greenert. Does anybody know Admiral Greenert? He's the new CNO, not so new for a while. And he's been talking about and writing about this idea of moving from platforms to payloads. Moving from platforms to payloads. And so the idea is instead of having an all-in-one luxury car platform, right, instead we have sort of dependable trucks that can handle a changing payload selection. What's a good example of that? Sorry? Okay. What's a good example of that in the civil sector? Intermodal is a great example. The other example is that little phone in your pocket. The platform supports now for each of the two major ecosystems, iOS and Android, there are now more than 1 million apps. That's a platform that is general purpose and robust. And by the way, the platform is evolving. It's not frozen in time. The incentives are aligned so that people want to participate. The network externalities, economics, all support it. Can we imagine doing that for configurations of systems? Well, so here are the mobile ones. Interestingly, this situation also exists for big data analytics. Hadoop is a framework, and a student can, in a matter of a week, create code that would fit on this file card that would do data analytics over petabytes of data. Why is that? It's because that framework is so powerful. Just like a student could in a month go from Gleam in the Eye to App in the App Store down here with cloud data and all sorts of features because the platform is so robust and wonderful. Okay? We don't seem to be able to do that in the defense world. Okay? So I've already pointed these points out about the significance of architecture. The challenges I just want to highlight. So the technical challenges, as we've talked about, have to do with modeling. But let me just focus on organizational challenges, which is, one is, the best way to go is the precedented way. If you can go on the paved road rather than having to kind of track through the forest, right? It's better, it's easier. Unless you really like the uncertainty of bushwhacking through the forest, but not so much for us, right? So we want the paved road. So if you've done it before, let's figure out how to capture that and use that again. That's part of the pattern story. But the other is this alignment, the complex law story of aligning organizational structures and supply chain structures with the actual system structures that we build. The pragmatics of architecture are really important. They drive a huge number of decisions. And, somebody mentioned IP and opacity and all that plays in here. Okay, and then the management of the boundaries. The opportunities are, I think, really significant that we could move in this direction of payload-centric design. The challenge is to create a business model that's going to work. By the way, there was a report from the PCAP, which is unfortunately the most senior panel of advisors in our government on science and technology. And the recommendation was to focus for cybersecurity on architecture as a pivotal driver. Why do I say unfortunately? I say unfortunately because the people they advise are in the White House, and they're not actually going to make systems engineering decisions so much. Maybe they will, but not so much. Okay, so agility, quickly. It's about practices and workflow. The point is to be able to be adaptive. A challenge is how do we make this work at arm's length? Internally, in the vendors, you go talk to anybody who works at Google, Facebook, Microsoft, Apple, Snapchat, Nike. I mean, these are the places where our students are getting job offers from, just what I'm thinking about them, right? They all have this highly iterative process. Microsoft for 20 years has already thought through the lessons of Fred Brooks' book and Mark Buckley's experience that we've alluded to today, which is how do we get to scale? You have an architecture that lets you break things up into a large number of small teams rather than a small number of large teams. Amazon does this. Werner Vogel, the CTO there. This is kind of the big accomplishment. And the Amazon cloud was a nice side effect of his architecture exercise. The challenge is how do we make this work and particularly at arm's length, okay? Lots of opportunities building on data, but also, and I don't have time to talk about this, we haven't even heard the phrase earn value today. What's wrong with that? But what I want to suggest to you for consideration is let's think about earned value let's get out of the box a little bit on earned value. And I'll call it the hat trick because it's got three pieces. And one is the usual thing of story point burn down or K-lock counts or whatever you want. Okay, but the other is I want to get a reward, and Barry has made this point often, for reducing uncertainty, narrowing the cone, reducing variance. You may not move the middle of the bell curve over, but if you narrow the bell curve, you should get points for that. And if you accrete evidence in support of assurance claims early in the process, you want to get rewarded for that too, because that reduces the uncertainties associated with integration and operational T&E. Assurance. Assurance is a really big deal. And the usual problem with assurance is we wait too long. Okay, and the fact that the whole point of this slide is to highlight the fact that others have finally figured out that assurance is really costing us big time. It's a big issue. The Defense Science Board has pointed out supply chain challenges. The PCAST report I mentioned. If you look at some civil things going on, the Toyota settlement, you really need to look into that. Ignore the enormous reports written online. Talk to people who are involved with that. It's a real eye-opener. Toyota has spent between $2 and $3 billion already in settlements because of what really very much appears to be software issue and systems engineering issue. It's a true systems engineering issue because it involves the relationship of a massive, incredibly complicated software connected with various sensors and actuators. Okay, and healthcare.gov has already been mentioned. So that's the point of that. So there are a lot of challenges here, and the evaluation practices are all screwed up. That's a real problem. Okay, after the fact, I mean, this is the worst case. After the fact, they don't handle any of these realities. Okay, it's a snapshot of the system. You can't do variability. There are at least 1,000 different versions of Linux just in the mobile ecosystem of Android. How are you going to get certification for that? No verification, and the IP issues are simply not handled at all. Okay? So that's assurance. Opportunities are very interesting. Opportunities have to do with getting into the semantics and getting connected in with the process and getting connected in with the design model very early and accumulating the evidence very early. When you think about architecture, you should be thinking about assuring the various claims that you want to make about the architecture, the outcomes of your architectural decision. And in fact, NITRD has started a new thread of thinking called design and security. And the interesting thing is, if you think about designing something to support an assurance evaluation, and I want to say T&E because people think T&E actually has to do with testing, okay? But if you think about that, it's actually going to affect the way we design our system. We're going to design the API so we can do testing at the component level, and we can integrate gradually, incrementally. Okay, so those are the three pieces. So the unhappy reality is that we, the engineers, share with the customer some really significant challenges. We can measure the I in ROI. We don't know how to measure the R so well. That's been our continual challenge. That's why quality practices are not so ingrained. That's why architectural practices are not so ingrained. That's why we don't know how to do incremental iterative development at arm's length. In fact, I've talked with folks and contractors, some of the not represented here, big guys, really big guys, not here though, who say, well, we pretend that it looks like a waterfall. We package it up for the program office like waterfall, but behind the curtain, we're actually iterating. You think, gosh, that's like not the way we want to be doing it. So arm's length is a problem. The IP issue is a problem. Acquisition culture, maybe we can fix that. Doing less development and more sustainment might be a helpful approach for the government. But I want to get to this one, which is the workforce training and continual technical. And the point I want to make here is, you know, there's a fair amount of gray hair in the room for those of us who have hair. And I want to emphasize that, and, you know, we're all here because we're all actively engaged. But I think there are a lot of folks who may not be so much. And we really need to focus on how to help the leadership understand these issues and the nature of the operating environment. These 3 points about architectural agility and iteration. So that's kind of my story. And my summary is that you really actually can have a vision that is very much a confluence of software and systems. It's like if systems were heading towards software, but in software we talked about Doug Schmidt is not here. But his folder is down in front, memorialized potential presence. And I'm sorry he's not here because he would be talking about that stuff. But that's the reality for a lot of software. When I say cycle physics, I don't just say control loops and standard control systems. I'm talking about a really complex system that interacts in many different ways with the environment. Okay, so you have the right kind of vision of how do you manage with high complexity and high uncertainty, but low project risk, let's just say project risk, and low system risk. That's the game. The game is to innovate safely. That's what we want to do. Okay? So here's the advice. I'm repeating it again. I've got 2 bonus slides in here, and then I'm going to stop. So anybody on Quora? Anybody tried Quora? So Quora was founded by somebody I know who spun out of Facebook, and he's gotten all the Silicon Valley moguls to ask and answer questions on this stuff. And so I got asked a question that I couldn't resist. I normally never think it. I have a Twitter account. I don't think I did. But I couldn't resist. And somebody says, well, what does it take for a computer science student to become a software engineer? And I thought, this is actually relevant to our discussion because it's important that it goes beyond point one here. Okay? It's also that we understand and respect the process and the people who participate. It's important that we understand the creative nature of what we do. Why is that? Because with software, if we've done it before, we reuse what we've got. So we're spending a lot of time being kind of creative and doing design. Okay? And by the way, we don't sit in the cubicle with that blank piece of paper. All right? If you're building a system, you want to go figure out what socio-technical ecosystems to participate in, what libraries to pick. And when I sit with undergraduates at home, the conversation is, well, I should do this library, maybe this library, or that library. And it's all about picking and choosing among these various components that are out there. That is to say, creating a supply chain that they feel comfortable with. So the amount of work that they have to do at the margin is tiny. And people thought software reuse was just simply never going to happen. And the reality is we now have pervasive reuse. It's an amazing thing. And it's partly the Butler-Lamson story, a very large component. But it's also that we've got APIs and we have components and we have rich supply chains, which is a double-edged sword, obviously. But what it really means is that a good software engineer is socially engaged. Because it's not just going out and sort of passively observing, it's engaging and interacting and learning about the life. If it's not alive, the project is moving forward, then it's dead. Okay, and staying current. So that's the one thing. And then the final thing is I loved Jeff Wilcox's list. And so I just have to sort of indicate there's, I think, a really nice congruence. I mean, I use different terms for things, but I'd say I just made up this slide during the morning session because I thought, there's so much confluence of thinking here coming from both sides. And I think that's simply because of this essential nature of software engineering. If I go back to this point here, this essential affinity. And that's the end of my talk. Thanks very much.
Bill, one great talk. I want to pull one specific thread. I'm hoping that you as a software practitioner can help the systems profession. And that is, as we try to undertake this move to models, which is still ongoing and will be for quite some time, one of the fundamental inhibitors is sharing. Sharing of successes, sharing of failures.
Yeah.
When you just talked about grand open source libraries and we don't recreate from scratch, that reflects a tremendous level of sharing. How does systems start to take that sharing step so that we can actually learn and advance?
Wow, that's a tough question, and let me respond to it in various ways. The semiconductor industry has gotten better at this. And they have more of a harness. They're in a much more they're in a more constrained harness, but they also have a consortium that's very active and very well funded, the SRC, and they create standards and models, and so the tool vendors are all building to the same models, and that's an ecosystem that's working pretty well. But the other thing I'll say is, if you go visit Microsoft, and it's easy to take pot shots at Microsoft, but actually, if you look at the first derivative from Microsoft of quality, it's probably steeper than most anywhere else, and that's because they've been incredibly aggressively investing in the development of models and reasoning capabilities and building those into tools that are usable by their own developers, because their own developers are their nastiest constituents, right? And so they have to fight the adoption battle. They can't force anything on anybody. They're not top down. They're aggressively bottom up. So they have to sell the tools to hundreds of different development groups. And that sales pitch actually works because they have a good way of constructing a business case. And I've not seen this happen so much in other organizations. And the interesting feature of that is they have an enormous diversity of models and an enormous diversity of tools, but the tools are integrated in a way that from the developer perspective, there's kind of this, an experience that makes sense. And the trick is the opposite of laundry detergent. So in laundry detergent, you understand what I'm going to say? But you don't. You add blue specks and it's revolutionary and new, right? right? With tooling, you want to do the opposite. You want to package revolution as evolution. So, you know, I build tools. Our tools, you got this wonderful huge screen of Eclipse. Oh, there's a little box down there that says, oh, well, you might be interested in this, right? An enormous amount, years and years and years of engineering and graduate students created that little box, right, which we packaged to be as minimal and unobtrusive as possible. But if you happen to click on it, it's going to tell you something useful, right? And so the way we package tools and integrate them into our process is really important. But the other thing is I think that firms believe that they, you know, Microsoft does not really sort of actively flog its tooling out into the marketplace. And you go ask them why, and they say, you know, it's kind of tough to build a business case around it because of the R problem, the R and the ROI problem. You know, the customers can't quite figure it out. I think this is a huge challenge for us. I said earlier, it's a big research challenge to figure out how to do the measurement. If we can make even the slightest bit of progress on that, then I think we could really get some kind of a tipping effect and get better, more useful tools. And since you asked about tools and you were talking about UML and SysML, you know, the problem with UML is except for state charts, it doesn't have semantics. It's just notation. It's suggestive notation, right? State charts has semantics, thank you, Dave Harrell, but otherwise not so much. And so the utility is really questionable. We want to have models that have meaning.
Bill, thank you very much.
Thank you very much.